Vesper stands for valence shell electron pair repulsions. It's a theory that we use to estimate shapes. It's based on the premise that valence electrons repel each other to make the atoms as far away from each other as possible. You're going to need to know this chart. If you have one bonding site and no unshared pairs of electrons such as HCl, the shape's going to be linear. We do not have a bond angle because we only have two items, which makes a line, not an angle. And no hybridization, or at least don't worry about it. If you have two bonding sites and no unshared pairs of electrons or lone pairs on the central atom, such as beryllium chloride, then it's also going to be linear. But beryllium, being our central atom, is our pivot point, and the farthest those chlorines can be from each other is 180 degrees. Hybridization, you need to remember that we have s, p, d, and f orbitals. S has 1 orbital, p has 3 orbitals, d has 5, and f has 7. So you're just going to start counting s and then p. You can count up to 3 p's. Water has 2 bonding sites, 2 lone pairs, so it's going to be bent with bond angles of 104.5 degrees. Atoms coming off in each lone pair counts for hybridization. So we have 4 things coming off, so that's S, P1, P2, P3. So it has hybridization of sp3. Okay, beryllium trifluoride has 3 bonding sites and no lone pairs. So the shape of this one is trigonal planar. So it's all going to be on one plane. So if it's in one plane, it's kind of like a circle is cut into thirds, and so each bond angle is 120. Hybridization, we have 3 things coming off. So that's S, P1, P2. I'm going to pause the video and draw the structure for an H3. H3 has 3 bonding sites and 1 lone pair, making it trigonal pyramidal. With bond angles of 107. And your hybridization is sp3. Notice that water and NH3 have the same hybridization and their bond angles are similar. You should know methane or CH4 by now. The shape of that one is tetrahedral with bond angles of 109.5. Your hybridization sp3. I'm going to pause the video and try to draw SF4 on your own. Your structure should have looked like this. 4 bonding sites, 1 lone pair on sulfur. And its shape is going to be seesaw with bond angles of 120 and less than 90. And your hybridization should be sp3d, because remember, P can only go up to 3, so the next one has to go to D. And D will be able to go up to 5. I'm going to pause the video and draw ICl4 -1. So that's your structure. And those lone pairs position themselves on the top and bottom, making this one square planar. With bond angles of 90. We have 6 things coming off, so our hybridization is sp3d2. I'm going to pause the video and draw PCl5 on your own. And it has 5 bonding sites, no lone pairs, making it trigonal bipyramidal. With bond angles of 120 and 90. 120 in the center, that's your trigonal, and then bipyramid, your top to center is 90. We have 5 things coming off, which makes it sp3d. I'm going to pause the video for BRF5. So you have 5 fluorines coming off and 1 lone pair, which makes it square pyramidal with bond angles of 90. Six things coming off, making it sp3d2. I'm going to pause the video and draw PF6 -1 on your own. So you have 6 fluorines coming off, making it square bipyramidal. Have a square in the center and 2 pyramids, top and bottom. It can also be referred to as octahedron. And your bond angles are still 90. 6 things still coming off, so still sp3d2. I'm going to pause the video and draw SO2 on your own. You have 2 bonding sites and 1 lone pair. This one is also bent, but the bond angles are going to be less than 120. Hybridization of sp2. And pause the video and draw ClF3. You should have gotten 3 fluorines coming off and 2 lone pairs on chlorine. This shape is T-shaped. And it has bond angles of 90 degrees. 5 things coming off, making it sp3d. Pause video and draw I3 -1. Two iodines coming off and 3 lone pairs on the central atom, making it linear. So the 3 lone pairs position themselves around the center, kind of like the trigonal bipyramidal, and so we're left with 180 degrees and sp3d hybridization.